Hello everyone, my name is Donghyun Han. I'm a PhD candidate at the IIIXL Lab. Today, I'm gonna introduce a paper titled Learning Time Critical Responses for Interactive Character Control, which was published at the ACM POG 2021. This paper is about training interactive character animation agent using a teacher-student framework. An interactive character can be controlled through user interfaces. The user input, which is either continuous or discrete, specifies a task for the character to perform. The authors focus on agility and responsiveness as a key attributes for developing interactive character animation. They define this concept as time-critical responsiveness. Time-critical responsiveness refers to the ability to perform motions accurately according to user input, while also completing the motion before a given critical time. Existing methods such as finite state machines and motion matching transition and replay motion capture data. These methods focus on optimizing motion transitions but fail to address time-critical responsiveness. Existing learning-based approaches can generate contextually appropriate motions from large datasets. However, they are designed in a way that makes it difficult to balance the quality of the generated motion with response time. The easiest way to reduce the response time is to playback motion data faster than the data were originally captured. However, this brute force speedup of the motion dataset could result in the character's motion data that looks hasty and unnatural. Also, to train the time-critical responsiveness, the author found that reinforcement learning alone is not sufficient to learn time-critical policies because of the structural complexity of the motion dataset. So they present a teacher-student framework to overcome the difficulty of the dataset complexity. Now, let's dive into the teacher-student framework. The teacher agent learns the optimal ways to achieve tasks, only allowing combinatorial operations such as splicing motion frames into a novel order. Once the teacher policy is learned, a student policy is supervisedly trained via policy distillation. Policy distillation is a process of extracting the policy of a reinforcement learning agent and training a new network that performs tasks at the same level of performance while being smaller and more efficient. Now let's look at the input of the teacher policy. The user input is defined by tuple U, which consists of A hat, T hat, D hat, and P hat. The one-up vector A hat represents the action type, T hat is the response time, D hat is the target direction, P hat is the target position. The target direction and the target position may or may not be specified depending on the action type. In such cases, they are set to 0 for unspecified values. Through motion matching, the best matching frame for the next time step is found based on the current state, and this frame is used as the target to determine each input. In other words, the teacher agent is trained using the motion dataset. For teacher policy training, the reward includes two terms. The policy receives a plausibility reward when it makes a transition from one state to the next frame state. This reward is achieved by computing the distance using the weighted sum of joint position differences and joint velocity differences between the current and target frames. The plausibility reward encourages smooth transitions between frames. While the plausibility rewards are received continuously throughout the simulation, the task rewards are received sparsely only when a task is completed. According to the task reward equation, D and P represent the current direction and the position of the agent respectively. The task reward is maximized if the goal state is achieved within the critical response time, and both the target direction and target position are met at that time. Finally, given a random state S and a random user input U, teacher policy generates a motion sequence and the reward is calculated based on this motion sequence. After the teacher policy training, supervised policy distillation process is conducted. The student policy is not an identical copy of the teacher policy, but the student policy achieves better responsiveness through policy distillation. For the student policy, critical response time is a controllable parameter. The student policy can have a continuous spectrum of responsiveness by adjusting the critical time input. Given an initial state S and a user counter U, the teacher policy generates an episodic motion sequence, which are time critically responds based on the motion dataset. However, we want to generate more variations to deal with controllable parameter tau for the student policy. To do so, the tau is randomly sampled from the range tau s to tau t and time warp the motion sequence based on the sampled tau. In this way, we can collect many tuples of a time limit and a motion sequence that performs a desired take within the time limit. The student policy is then trained in a supervised manner to follow these time-warped motion sequences. The student agent takes the current state st and user counter ut as input and outputs the next state st plus 1. The state of the student agent is represented as a tuple S, which consists of rt, rd, jp, jr, c, and a. RT and RD are the position and direction respectively of the skeleton root on the two-dimensional plane. JP and JR are the aggregated vectors of joint positions and orientations respectively. C is a vector of binary flags indicating body ground contacts at the end effectors. And finally, A is a one-up vector indicating the activation of an action. The student policy can be learned from the rich collection of experience tuples st, ut, st plus 1 generated by teacher policy. The loss function includes three terms: E motion, E contact, and E rigid. The motion term E motion penalizes the discrepancy between network output and training data. State S hat and state S respectively are the observed state from an experience tuple and the corresponding network output. The contact term E-contact penalizes foot sliding. K is the joint index and CKT is a binary flag that indicates if the joint K is in contact with the ground plane at time t. HKT is the joint position in the reference coordinate system. The rigid term E-rigid favors that the lengths of the body links are preserved, since the student policy operates on kinematic animation. The two connected joints K and M are connected by a rigid link, and LKM is each length. They trained policies using TensorFlow for deep network operations and Unreal Engine for characterization, interactive control, and rendering. The teacher learning takes 12 to 24 hours in the computation, while the student learning takes 4 to 8 hours using single GPU PC. You can see the types of agent they trained and the included action types in the table below. Among these, I'm going to review the evaluation results of the locomotion and the martial arts agents. Let's take a look at the evaluation results of the locomotion agent. The figure above is a completion time plot for a locomotion task. The red line represents the given critical response times, while the blue line represents the expected completion time based on the given turning angle. We can observe that the blue expected completion time curve does not exceed the red completion time line in all critical response time. The video below shows that the locomotion agent can turn at various angles within different critical response times. The figure above shows that completion time for each action type in the martial arts agent. Similar to locomotion agent, we can see that the maximum completion time and the mean completion time for all action types remain below the critical response time. The video below shows that the martial arts agent can conduct various actions within different critical response times. In conclusion, previous research has faced challenges in balancing motion quality and responsiveness. To address this, the authors use a teacher-student framework to train an interactive animation agent capable of achieving time-critical responses. However, there are some limitations. As the response time decreases, the motion quality degrades significantly. Additionally, while supervised learning enables time-critical responses in kinematic animation, it becomes difficult to adapt to external impacts or environmental changes. Thank you for listening.